responsible for all their compute, multimedia, and graphics cores on their SoCs. As you know, MediaTek is one of the fastest growing companies, especially in the Far East with their SoCs. He has a very impressive lineage in processors. He used to be at Silicon Graphics, Transmeta, Rendition, and NVIDIA. So he's basically covered the spectrum. And he actually did his PhD in computer science from Yale University, and he developed something called the orthogonal iteration estimation algorithm for pose estimation, which is one of the most widely cited algorithms in computer vision and augmented reality and robotics. So when we were reviewing his presentation, he's very particular that he hits home on a few key messages. And the reason he does that is, he says, when he was a PhD student at Yale, his advisor made him take a class on neurobiology, which was mainly pre-meds and biology students. He was the only EE student there. And they spent half the semester on circuits. Obviously, he aced it. The second half was on biology. And so he applied himself, and he actually aced the second half more than he aced the first half. So he was feeling proud of himself. And a few years later, when he was doing chip design, he said the only thing he could remember from that class was a key neurobiology principle, which is use it or lose it. That's all he remembered from a full semester of really hard study. So his point is, when you deliver a message, hit some key points home, because that's all the audience remembers. And to do just that, let me welcome Dr. Chien-Peng Liu.
So today, we're probably first going to talk about something interesting actually not about computing, but about English. So it's quite fascinating that a group of animals is called in English. So before you type your laptop onto search for Google, I'm going to go through the slide pretty quick. So a group of hippo is called a crash. And a group of cross is called, somebody, if you know some novel, you probably know about it. It's called, yeah, okay. So you got it. Okay, you're faster than me. Okay, then a group of giraffe is called a tower. Okay, this is kind of funny because what you see actually is a couple of towers here rather than one tower. So it's not very intuitive. But, so it's not surprising that we use a parade or elephants, a herd of sheep, and an army of ants. But here I'm not going to talk about animal kingdoms because the list can go on and on. So I'm going to talk about processor cores, which actually is as fascinating. So we need to flashback to years of 2005. So over to 2004, some people have different way of talking about the time, but it doesn't matter. So the point is that we hit the power wall. Okay, so we could no longer cool down a chip economically. So in order to stay at the same power, so the industry has to switch gear. So they have to replicate number of cores on the chip. So hope that the parallel computing will save the world, save the Moore's law. Okay, this is what happened. So we'll expect to see that we should go from, say, dual core, quad core, and eventually, if the number of core grow exponentially, we should be able to quickly see hundreds or even thousands of cores. That's why I keep coding it as a sea of cores. Okay, so when you start out as a dual or quad core, things should be quite easy because you don't really do things very differently when you have a single core. But as times go, the things will become, the things you see actually become a totally different beast. So the question is, are you going to use all the core or not? So the question is, how many core will we need? And according to a theory called dark silicon, the claim is that eventually the number of core we can use on chip will be like tiny drop in a sea of cores. So here is how it goes. So say going from 2 to 4 cores, you can only power 3 of them. So your performance will drop from 4 to 3. Then when you have 4 to 8 cores, and if you can only power half of them, then your performance will drop. Your speed up actually will drop from 8 to 4. And when you go from 8 to 16 cores, if you can only power a quarter of them, then your performance will drop from 16 all the way to 4. So notice that the major things happen is that you can no longer see any performance gain with additional cores on chip. Okay, so remember that it's not because we are lazy. It's just because we cannot keep up with the exponential growth in the core count. So if this is true, then actually Moore's law and as well as the economy that depends on it will like heading toward a train wreck. So if that's true, actually we probably all come to the wrong conference. Okay, so we probably should try to figure out where else we should go. But before we pack and go, I'd like to probably take a deep dive into the theory just to see what it is saying. So let's use a chart such that you will help me to visualize the situation. So we can use the vertical axis as the power and the horizontal axis as the number of cores. So of course, first of all, we have a power ceiling. So this is a power boundary that we cannot pass. Everything above will become dark. That's why we call it dark. Okay. Then for any special kind of core, we're going to use a line to indicate how the power grows with the number of cores. Okay. So as you can see, what we really want to see is a line as flat as possible, such that when the number of cores grow, you don't have to hit the ceiling. So, however, this is not what the theory is just talking about. So, in addition to the power ceiling, we also have a parallelism wall. Okay, so this means that we're confined in a room, bounded both by the power ceiling and parallelism wall. But we have to pay attention that actually these two limitations actually is quite different in nature. But somehow, the situation as being bounded in a room is generally referred to as power limited issue in theory. But this theory does tell you something very important, is that we really need to change the way we define the cores. Because our core today is just not, the line is just not flat as possible. We need to make it flat. But the problem is that we still need to keep our current workload going. So we cannot make this all flat. So the way we're going to do is actually to replace the line with several segments. First of all, with some big cores, which I refer to as a parade of elephants. Some little cores, which I refer to as a herd of sheep. Then, we can make room to host a huge army, what I call is an army of ants, okay, which consists of GPU-style cores. Of course, we know that this kind of arrangement actually works today because we have been seeing so many with what we call heterogeneous processor around the market, and they work quite well, including the APU that you have been hearing about. And actually, many of the mobile SoC, the come from MediaTek, actually is also have this kind of arrangement. So, sounds like we have a solution, right? So we are saved. We can all stay here for the next 2 days. But however, somehow the theory doesn't stop here. So they go on and claim that the cores beyond the parallelism wall are also dark. Okay. What's the reason? Because beyond the wall, if you add any additional cores, you won't improve the performance. That should sound quite familiar, right? This is exactly the AMD's argument against parallel computing in 1967. Right now, has been used again, okay, but in the name of a power. So the issue is here. So if you think about the workload like body tracking or H.264 encoding, the parallelism wall is here. Okay, here actually. Then if you think about something like ray tracing, then parallelism wall will be pushed out all the way to the left. It's right here. So all of a sudden, the core got lighted up. So there's a funny situation is that we'll behave if we will stick with the body tracking. And if we will all choose to work on ray tracing, then we are fine. So it's kind of interesting that when we predict the fate of the industry by what kind of workload that we would like to run. So is this easier? Actually, we just try to ask the developer or the programmer try to find something like ray tracing to work on. So let me summarize. So the issue is that the theory started out as a concern on power, I think, which make a lot of sense. So that's why that triggered the whole industry to think about what's the right definition of the cores. I think that we come up with a good solution. But then the argument turned out to be an argument against parallel computing, which is exactly the same way as AMD's law. So here I'd like to probably go back and revisit AMD's law again and to see whether it's how we can use trend prediction. Okay, so here I try to formulate AMD's law quite differently. So this is not what you see in your textbook. Okay, so I try to draw different curves with different problem size. So I think it's good for general for data parallel workload because the problem size scale very easily. Okay. Then, so here you can see there's a three curve for problem size equal to 16, 64, and 256. So by the way, all the numbers here are relative, so don't worry about it. It's not an absolute number. Then I try to account for the communication overhead. Otherwise, it will seem to be too optimistic. And this communication overhead will be proportional to logarithm of number of cores. So as you can see, when the number of cores exceeds some threshold, then performance is not just flat plateau. Actually, it starts to drop. So here we can see a situation here because such a curve can never be used for trend prediction. Because for any trend prediction, the curve should keep going up. So one of the issues here is that actually the horizontal axis is actually not time. Okay, it's just number of cores. It is what it is. So, but if we really want to use the horizontal axis as time, there's one way we can use it. So for each tick should represent a point in time when the corresponding number of cores become affordable. Okay? So let's use it as a time axis. So say when 16, 64, or 256 core become affordable. So what will users do when they look at the curve? So for me, I would definitely pick which is best to use, to leverage, to justify the investment of more cores. So we'll pick 3 different points at different curves. So if we really want to do a trend prediction, actually what we should actually is to connect all the decision points across the number of curves. Then we'll see different curve here. Here, let me just show the curve at full range. Just remember, actually, the speed up is log scale. So as we can see, a straight line in the log scale diagram actually represents an exponential curve. So this means that actually the speed up can really grow exponentially as long as your problem size scale as a number of cores. So really up to our choice. Okay. However, there's one problem because why bother actually creating? So here, let me try to use some example. So the first one is coming from MediaTek face beautification. So this is a photo of a lady. Actually, I think the photo is quite nice, okay, from without any modification. So if we apply some techniques such as skin tone adjustment, wrinkle removal, then you will see a different picture. And let me tell you that actually this algorithm actually runs reasonably fast, even on our popular low-end application processors. Okay, this is one of the coolest features in our product. And just imagine when this lady pick up a new smartphone, what would she like? Would you like to have this skin tone adjustment and wrinkle removal run twice as faster? Because it's reasonably fast already. So how about we add another set of features? We can make her face thinner, make eyes bigger. So when it comes to beauty, there seems to be no limits. But after saying that, actually, I have to say that actually, maybe for guys like me, there's really some kind of limit there. So maybe AMD's law really apply. Okay, that's for different situation. Okay, so here, take a look at another example. Let's talk about graphics. So anybody know about this screenshot? Good. So I know there's a lot of people, some people keep silence. So let me tell you. So if you don't know, then chances are that you are among the very special 6% of American consumers who don't know this Pac-Man. Okay. This game actually is probably considered perhaps one of the highest grossing video game of all time. It was created in 1980. I just remember that actually at its 30th anniversary, actually try to replace, just put a playable version of the Pac-Man as their Google Doodle. And that day, actually worldwide, the enterprise worldwide actually lost 4.8 million working hours. Okay. But given all its glory, I don't think any game developer or GPU architect will make a living by sticking with it. Okay. We all love it, but the problem is that time has passed. We simply want to do more things in 1/60th of a second. For example, it's not very interesting to say the Pac-Man, we can run Pac-Man at 500 frames per second. It probably cannot. And if we use the dark sequence theory, the game industry, or even the graphic hardware industry, has already hit a train wreck a couple of years ago, or maybe 10 years ago. So, in the graphics area, we try to keep moving on. For example, in the mobile graphics, is one of the probably fastest growing the industry. So as you can see, we can see the environmental map used in 2011, and we see bump and specular maps used in 2012. Then we start to see motion blur in 2013. And from now on, we just going to see a lot more light, like 60 lights with different shading. So we're going to see a lot more interesting happen in the graphics. So graphics keep moving. Okay. Then in the area of high performance computing, we see a very similar trend. So the top 500 from 1993 to 2012, the gigaflops increased by 130,000 times. And clock rate only increased by 10 times. But in the same period, the number of cores grew by 11,000 times. And if you see a chart, you will find that actually the number of cores decreased a little bit when the clock rate rise. But when the clock rate stopped, or even start to keep a count just steadily. So as you can imagine, so when the scientists can shorten the time for their task from, say, from months to weeks to days to hours or to whatever they feel reasonable or comfortable, they won't just stop there. They'll go out and look for bigger problem. Say they try to simulate more atoms at a higher grid resolution and in more time step. So let's go back to Moore's law. So the older Moore's law gives us higher frequency, which allows us to write more complex software. Consequently, the user experience. And in turn, it should trigger more investment back to Moore's law, and the cycle should repeat itself. But now, instead of higher frequency, we got more cores. Okay, what should we do? We know that we need to create a bigger problem. But how do bigger problems lead to better user experience? Okay, it's quite obvious in the graphics and the HPC world I just mentioned, right? Because if you create a bigger workload typically is data parallel workload. With more triangles, with more effects, you will make gamers happy or happier. And if you make real world to include more items, you will make scientists more satisfied. And sounds like we already completed the loop. But unfortunately, somehow in this industry or part of the industry, somehow they still cannot or not ready to recognize such a workload as a mainstream. Maybe they feel that the community of gamers and scientists, sorry, no offense, if you are one of them, is too small to be influential, to be able to mainstream enough to drive the whole industry. So, but however, there's another phenomenon that's happening now, which is the data. As we know, the data has been grow explosively. And actually, in certain measure, actually it's outgrow the Moore's law. So why don't we think about how we can feed this driving force back into the loop, such that the engine can start, can keep running. So then the question we'd like to ask is, what bigger data to solve with bigger data? Sorry, what bigger problem to solve with bigger data? And how solving bigger problems lead to better user experience? So one answer, obviously, is try to find something from data. So that's why I call, this is the reason why the data mining has become so hot. There's another name is called it as a data analytic. And I like to call it machine learning because this is my background. So let me show you how these things work. So this is a very interesting interface. This interface will ask users try to select a cat photo, probably 6 of them or whatever, from the 12 photo of cat or dog. Okay. And this program actually is meant to protect the website from malicious program like bot. The reason you will be effective is because definitely, or at least for now, no program can do a better job than human. So why is it hard? Because sometimes, of course, the dog and cat can be viewed from several different angles. And sometimes there's more than one cat. And sometimes there'll be a dog in the foreground and cats in the background. Okay, and most of the time, there are simply so many distractions. So how do we solve this problem? Okay, sorry, I'd like to show another photo. I'd like to see whether there can be also a program can actually relate all the different photos from the same dog. Okay, for example, you can help to find the missing dog. And actually, this is my dog. Okay, the left picture actually is taken when I was away for a business trip for 1 month. So he looked quite messy. And I cleaned it up, and you can see there's a photo in the right. Okay, so how do we solve this problem? So I'm going to search for a theory between dog and cat. I said nobody knows about this kind of theory. So the best way actually is to present, to try to find something from a lot of photos. For example, there's a website called kaggle.com. Actually, they try to set a contest for a contender to come up with some kind of algorithm. And they'll offer 12,500 photos labeled as dog, and the other set labeled as cats, and will present to you. So imagine, they don't ask you to study the photo, because you already know. Your brain already have tons of dog and cat images labeled by your parents from your childhood. So the photo is meant to be fed to a brainchild, a machine learning algorithm. So how does it work? So it's like to finding a model that will map X to Y. Then X can be dog and cat photo, and the answer can be either the photo is a dog or cat, or the X can be sensor images, sensor reading, and the Y can be whether you are jogging, walking, or climbing. So the trick is that you want to find the knobs, because the model doesn't know anything about calling a dog and cat. It doesn't know anything about sensor reading. So you need to find the knobs. So for a very complex problem, you need a lot of knobs. But the problem is that a model with a lot of knobs will become jack of all trades. However, thanks to the current data explosion, we have tons of data can be used to tweak, to come up, to determine the set of knobs. And the number of knobs can grow to millions or billions. But thanks to big data, right now we can solve it. So, jack of all trades can become a master of something, given enough data. And with enough knobs, then a powerful model will lead to better user experiences. Okay, now, I'd like to emphasize the importance of the client in this big picture. So the data really comes from the client. So when the client feeds more data back to the cloud, we'll have a much bigger training set. Hopefully, you can do a much bigger data mining in the cloud, which means that cloud also needs a bigger parallel capability. Then we can start to dig out more smarts. And those smarts can be delivered to client and make clients smarter. And at the same time, we'll invest a better sensing such that we can keep much more data. For example, our much more sensor reading on our body, or better connectivity back to the cloud, and even local machine learning, such that we can tune to each person. The future is really here. You don't have to look into the distant future to find with a massive number of cores. There are already massively parallel heterogeneous processors around. And there's really no shame to be data parallel, because I consider one of the smartest things achieved in the computing is authentically data parallel, which is what I show here is a Google Brain experiment. They used a model with 1 billion parameter trained with 10 million images. And somehow the model can come up with the concept of cats or the human face all by itself. So look forward. We need to make a client much more smart. Then the data center need to process more, need to be able to feed more bandwidth hungry and smart client. So actually we have issue at data center as well, because the carbon footprint of US data center actually is at the same level as airline industry, which means that the data center is as dirty as taking all the jet line to the air. So we really need to, in order to meet all the performance requirements, we need to go parallel. And in order to go parallel, we need to go heterogeneous in order to keep the mobile device cool in our palms and the data center clean for our environment. Thank you.